Hello everyone. So today we are going to discuss the problem of the day for the geeks for geeks. And the question is nearly sorted. So you're given an array where each element is at most k away from its target position and you need to sort the array optimally. Okay, so we don't have to use the STL sort. We don't have to use the inbuilt sort functions in order to sort the array. And the array is given to us. And one more additional information is given to us. Whatever the test cases that you will be having, the element will not be away by more than k. Okay, so it is at most k away from its target position. So when in a sorted array where the element is supposed to be, it will not be away from its target position by more than k. So let's see an example. So if you see 2 in this example, its target position is supposed to be this position, right? And if you see over here, it is 1, 2, 3. 3 distance away from its original position, right? Similarly, 5. The target position of 5 is over here, right? Which is at the third place, but in the original array it is at the second place, so it is just a distance of 1 away, which is still less than k. So it is at most k distance away. Okay, at most k away. And we have this information, it can be k to the right or it can be at a distance of k to the left of its target position. Okay, and we need to sort the array optimally, so we have to somehow optimally sort the array and not use the stl sort function. Well, an approach that might come to one's mind is we simply sort the array without using the stl function, and we will be able to do that in n log n, isn't it? But our time complexity should be better than n log n if they are really asking us to sort the array optimally. So let's think about it. So what is the information that's been given to us? The information is that the element is at most k away from its target position. That is the crucial information that we have. Okay, so we can take a window of size k, right, and keep on sorting that window. Okay, so for example, if we look over here, okay, so we have 6, 5, 3, 2, 8, 10 and 9, right? Remember, 2 was supposed to be here, right? So we take a window of size 4. Okay, we take a window of size 4 for this particular example where the value of k is 3. In general, we will take a window of size k plus 1. So this is our window of size k plus 1, i.e. of size 4, 6, 5, 3 and 2, isn't it? Now we will first focus on having them sorted. Okay, so their sorted version will look something like 2, then comes 3, then comes 5, and then comes 6, isn't it? This is their sorted version. So after dealing with this window, we are sure that the smallest element of the array is going to be in the first window of size k plus 1, isn't it? So we will assign this 2 to the very first element of the array. So let's take our array and we will assign this value 2 to the very first element of the array. 2 is going to be for sure the very first element of the array. Okay, so now let's erase 2 from here. Now we will move ahead and include 8. Okay, we will include 8. So we push in 8 over here. Okay, so after pushing 8, it again should be able to sort these elements and push the smallest element at the top. Okay, and the data structure that we are using in order to have these k elements, it should be such that we should be able to access the smallest element from it, isn't it? So since 3 is the smallest element, so we will be able to access the 3. So what data structure comes to your mind when talking about this, that we should be able to access the smallest element? Well, obviously the priority queue or the min heap, isn't it? We can also call it min heap. Okay, or a similar data structure that we have is the multiset. Okay, the C++ coders will be familiar with it, but it is similar, very similar to the min heap. Okay, so we need to be able to access the smallest element from this, right? So the smallest element now is 3. So let's just access it, okay, and send it to our array. Okay, this is our array now. Okay, remember we were done up until 8. Now we go to 10. Okay, and we push in the 10, and now again we search for the minimum element in this particular window, and the minimum element is going to be 5. So let's just send this 5 to our array. Okay, now after dealing with 10, we go to 9 and we push in the value of 9. Okay, and our loop ends, right? Our loop ends here. Now this is going to be our final array, right? but it has not yet included all the elements of the original array, because our original array was of the size 1 2 3 4 5 6 7, isn't it? And here we have inserted only 3 elements. Well, the remaining 4 elements are there in this particular min heap. Okay, so we need to be pushing these elements from the min heap to the array, isn't it? So we can be doing that. The smallest element in this window is going to be 6, so we push the 6 over here. Okay, and now the smallest element is going to be 8, so we take the 8, and then the smallest element is going to be the 9, so we take the 9, and then it's the 10, right? And that's how our array gets sorted. Now the question is, even a min heap takes a log n of operation while taking an element out of it or inserting it. So how is not that making our code n log n? Well, the reason is because this maximum size of the min heap that we are having at any time is of size k plus 1, right? We are not having the size of the min heap is as n, isn't it? We are performing this particular operation of pushing and taking out the elements of the min heap every time as we move along the array. So this is n, okay? And every time the size of the min heap is k plus 1. So it is n log of k plus 1, the total time complexity. So instead of n log n, our time complexity is n log of k. And that's how we have optimized the code. Remember, k was always less than n or equals to n. So our code is optimized. And instead of n here, we have k, and k is less than or equal to n. So that's how our code is optimized. Okay, now let's go ahead and code this up. So first of all, we need a min heap. Okay, so I'll be using a multiset. Okay, because I'm using C++. It works very similar to min heap, which works similar, in fact, to set. What's the difference between a set and a multiset? It allows for duplicate elements as well, and it sorts the element that is contained within it. So that's your multiset for you. Now, first of all, remember, we need to store the k plus 1 window in this multiset. So let's start and store those k plus 1 elements. So we'll insert. So we'll insert these elements. Now that we have created this window of size k plus 1, we start from the next elements and we go till the end of the array, isn't it? Now in this multiset, we first of all find the smallest element. The smallest element is going to be the very first element of the multiset, right? So let's just find out the smallest element. It's going to be at the beginning. So it's m.begin, and we need to find its value. So we'll add a star before it. Okay, this is going to be our smallest element. Let's now just remove this smallest element from the multiset. So we'll just erase the element at the beginning. Okay, and we'll have a new array in which we're going to push this smallest element, right? So we need to declare this array as well, this array called the result. Okay, so let's declare it over here. After doing all of this, we need to push in the new element. After we have done traversing all over our loop, if our multiset is not empty, and for sure it will not be empty as we have done the dry run already. So what we are going to do, we're going to repeat this process. We're going to find the smallest, we're going to erase the element that is at the beginning, and we're going to push it into our new array. Okay, and we will keep on doing that until our multiset is not empty. Okay, and when it's empty, it means we have pushed all the elements in our new array. And since it's a void function, we don't need to return anything. We just need to change this array of ours. So we can change this array to result. Okay, now let's just run this code and check. Okay, so it's throwing an error. N was never declared. So we have never declared the size of the array as n. So let's just declare it. So n is basically add.size. Now let's run the code again. Okay, so it's working fine. Let's submit the code. Okay, so we are able to solve this problem successfully. Now, if you see, we have used extra space, right? An extra space of the size n, because there were n elements in the array. This will make our space complexity as O of n. Okay, so how do we avoid that? How can we make our space complexity as O of 1 only? Okay, so for that, we need to change this array only, right? We need to change this array in place. So let's just play with index. So let's have an index that is pointing at the beginning of the array. Okay, and now as we find out the smallest element in the multiset, we are pushing the smallest element in the result, right? Instead of pushing it into the result vector, what we are going to do is, let's remove this line. We're going to assign the array of index, this idx, as the smallest element. Okay, and we'll keep on increasing the idx. So that's how, just by playing with the pointers, we can manage our array updates. And similarly, we need to be doing that over here. Instead of pushing into the result vector, we will be doing this. Okay, and finally we don't need to be doing this. Okay, and we can just remove this result vector. We don't need this. So now our space complexity will become O of 1. Let's compile the code, and it's working. Let's just submit it. So we are able to solve this problem. The time complexity is n log k, and the space complexity is just O of 1.